Welcome to Engineering Systems. Today, we're continuing our availability pattern series. Now, if you caught our previous explainer, you'll remember we broke down exactly what availability means, right? We looked at why uptime matters, how those availability percentages actually translate into hard minutes of downtime, and why building highly available systems is absolutely critical for any modern business. Okay, let's dive into this next crucial piece of the puzzle.
Here's our architectural blueprint for today's explainer. We're going to quickly revisit the availability equation, formally define single-point failures, analyze a fictional FoodDash outage, expose some hidden dependency chains, talk about operational failures, and then wrap things up with our next steps for high availability.
Section 1. The availability equation, translating uptime into reality. Remember why we're so obsessed with this stuff. Those uptime nines we calculate, they aren't just abstract math. They are the literal difference between your business running or being completely dead in the water. Which naturally leads us to an incredibly important question. Why do systems actually go down in the first place? I mean, if every single tech company on Earth wants high availability, why are we still constantly seeing major outages in the news? Well, the answer is surprisingly simple, and it comes down to practical engineering reality. Most outages do not happen because absolutely everything in the architecture fails at once. It's almost never a total, simultaneous system collapse.
Section 2. Defining single-point failures, the component everything relies on.
Instead of that total collapse, outages are incredibly often caused by just one critical central component failing. We're talking about a single web server, a lone load balancer, maybe a single network switch, a specific cloud region, or even a third-party service. It's that one thing that absolutely everyone relies on. And that brings us to our core topic. A single point of failure, or SPOF as you'll hear it called, is basically any component whose failure causes the entire system to become unavailable. In really simple, intuitive terms, if this thing dies, everything dies. To kind of build a conceptual foundation before we get into complex architectures, think about your home's electrical wiring. Imagine your entire house gets its power through one single main breaker. If that one breaker trips, the lights go out, the ceiling fan stops, the internet router dies, the fridge shuts down, you get the idea. Every subsystem depends on that one component. That breaker is a classic single point of failure.
Section 3. The FoodDash outage case study, a realistic evening dinner rush. To really ground this engineering theory into practical reality, let's look at a high-stakes scenario using a fictional food delivery platform we'll call FoodDash. Imagine a typical Friday evening dinner rush. The platform is humming along perfectly. Step 1, hungry customers are swiping through the app and successfully placing their orders. Step 2, partner restaurants receive these digital tickets and furiously start prepping meals. And Step 3, delivery partners out on the road are accepting requests and routing to the restaurants. It's this beautifully orchestrated dance of distributed systems. Everything works, customers are happy. Then, without any warning whatsoever, the central database server completely crashes. Suddenly, users can't log in, new orders instantly drop to zero, payments completely stop working, and this brilliantly illustrates our core concept. The backend web servers, they're actually still running perfectly fine. The front-end mobile app on the user's phone is fully responsive, but the platform is effectively dead because every single request relies on that one database to process the transaction. That single component paralyzes the entire business.
Section 4. Exposing hidden dependency chains when redundancy is an illusion.
Now, what's really interesting about this slide is how it shows that spoofs aren't always obvious. Sure, it's easy to spot a solitary database and say, aha, that's a spoof. But these vulnerabilities notoriously hide deep within systems that look highly redundant. Check out this direct architectural comparison. On the left side, we have an obvious single point of failure. One web server, one database. If either goes down, boom, immediate outage. But look closely at the right side. We've got two web servers now. Engineers will often spend months scaling this application layer, right? Adding auto-scaling groups, setting up intelligent load balancing. It looks fantastic, it looks resilient. If one web server catches fire, traffic seamlessly shifts to the other. Great, but they both still point to just one central database. Adding redundancy in one layer does absolutely nothing to eliminate the spoof in another layer. That database remains a catastrophic single point of failure.
And it goes far beyond just your own infrastructure. Modern systems are these incredibly complex webs of interconnected dependency chains. Let's walk through this e-commerce breakdown. If your front end fails, the user interface breaks. If the back end goes down, the core business logic fails. If the database crashes, transactions stop. But look further down the chain. What about your third-party dependencies? If your payment gateway vendor has an outage, your checkout process is literally blocked. If your email service provider goes down, digital receipts fail to send. A modern system's availability depends entirely on every single one of these critical links functioning correctly.
So how do engineers actually find these hidden traps? Well, we use a very specific, vital engineering heuristic. You have to look at your architecture diagrams and relentlessly ask, what happens if this component suddenly disappears? Take every piece of that FoodDash architecture we just looked at. What if this particular server dies? What if this central network switch loses power? What if this specific cloud region becomes completely unavailable? If the answer to any of those is the entire system stops serving users, then bingo, you've successfully identified a hidden SPOF. Section 5. Operational and human failures. SPOFs aren't always technical. Up until now, we've talked strictly about servers, networks, and databases. But we have to shift our perspective here for a minute, because organizational bottlenecks and human processes can create massive business risks that are just as dangerous as a failing hard drive. This quote really hits the nail on the head. Good engineering isn't just about infrastructure. It's about eliminating dependency on any single component, process, or person. Imagine you've built this beautifully designed, highly redundant cloud architecture, but only one engineer in the entire company actually understands how the deployment pipeline works. Or maybe only one single individual holds the sole access credentials to the production database to run a recovery. If that person is on a flight or unreachable during a critical late-night crash, your business literally cannot recover. That right there is a massive operational single point of failure. Section 6. Designing for high availability, identifying SPOFs is step 1. So, the crucial point is this. Actively finding these technical and human single points of failure is the foundational, non-negotiable first step in availability engineering. Before you can even begin to design complex, fault-tolerant architectures, you have to know exactly what vulnerabilities exist within your own walls. You absolutely must internalize this concept. Every single point of failure creates an additional way for your system to become unavailable. The more of these unmitigated dependencies you have, the more fragile your platform becomes. Modern systems have to be designed from the ground up to minimize these critical dependencies. You've got to comb through your infrastructure, your software logic, your third-party vendors, and yes, your team's internal processes to systematically root them out. So let's wrap this up and look at our path forward. What did we learn? First, a single point of failure is any component whose failure can bring down the entire system. Second, these SPOFs are sneaky. They can exist in infrastructure, software, external dependencies, and even in your people and processes. Third, we have to design modern systems to minimize these critical dependencies. And finally, identifying these SPOFs is step 1 toward high availability. This builds directly on our previous availability lesson. Next up in our explainer series is redundancy, the first step toward high availability. Now that we understand exactly what brings systems down, we're going to learn how engineers eliminate those risks. Thank you so much for tuning in to Engineering Systems. Please hit that subscribe button so you don't miss the rest of our availability pattern series. Until then, I want you to ask yourself, what is the one hidden component your entire architecture is secretly relying on right now? Think about it. I'll see you in the next one.